We'll go ahead and get started. My name is Tyler Croy. Thank you all for coming here. There's a Unity session happening right now, so I'm glad you chose this one, because I was also kind of curious to go to that Unity session. I helped create the Delta Rust project at Scribd, which is my day job. My night job is working on Buoyant Data, which is where I created some of the software that we'll be talking about today, and how I've come to use Delta in Lambda and a lot of other sort of small constrained environments. I should note that I've also authored the chapter in the Delta Lake Definitive Guide from O'Reilly, which is in, I think, preview release now. I don't entirely understand the life cycle, but a lot of the things that I'll be talking about today are also going to be contained in that book, and we'll focus on both Rust and Python, which is most of where I'll be spending time. So let me define the terms real quick. When we're talking about Delta Lake, I hope many of you are already familiar with Delta Lake conceptually. Maybe you're already using it. But at its essence, at its core, Delta Lake is just transaction log files, typically JSON files, on disk in an object storage, whether your file system, S3, Azure's data store, whatever it's called, or GCS, whatever. And then data files. And those are typically, I would say, conventionally stored in Apache Parquet format. They don't need to be stored in Parquet format, but they are. In most implementations, they're stored in Parquet format. And what I've got up here is a completely contrived example of what a Delta table looks like on disk. You'll typically have your Hive-style partitions, and in this case, we've got a date stamp partition of 2024-04-01, April Fool's Day, with a couple of data files in it, and then a 04-02 date with a couple of Parquet data files in it, and then a single transaction file in the Delta log. For a lot of my examples, I'll be talking about the JSON transaction logs. But one thing to keep in mind, especially when we're talking about higher performance or lower resource constraints with Delta logs, is there's also checkpoint files, which are compressed Parquet files, which you will need to be considering if you're deploying larger scale or higher throughput Delta Lake Lambdas. And when we're talking about Lambda, most of the experience that I have is working from the Rust side of things. You don't necessarily need to use Rust. One of the beautiful things about Lambda is you can kind of build an AWS Lambda in just about anything. It's fairly easy to do it in Python. You can actually just go straight into the web console and start writing Python. What you can't do, unfortunately, is you can't go straight into the AWS web console, start a Python Lambda, and start writing code that will interact with Delta Lake. There is a layer in AWS Lambda terms called the AWS SDK for Pandas, which includes some of the dependencies, but it does not to date incorporate the Delta Lake Python package. If you're using Rust, I recommend the Cargo Lambda tool, which you can pip install. One of the important things about Lambda is that, like all things in the cloud, time is money, and there's some specific axes upon which cost really impacts your Lambda. Execution time is the most important one. If you can run faster, the difference between 1 second and 100 milliseconds is consequential with your runtime. If you can run it in 10 milliseconds as opposed to 100 milliseconds, that's even better. Memory is also a very important component to Lambda. If you think about how AWS is scheduling all these workloads, if you have a Lambda that uses less memory and can run really quickly, that means they're going to be scheduling that on the underlying EC2 instances, and they can pack a lot more in there. So they are incentivizing you to use less memory. And that is to your advantage if you're using Python, or especially if you're using Rust. It might get trimmed off down there at the bottom with the captioning. I did not expect captioning. But it says storage. Storage doesn't really matter with Lambda. You technically are charged for it, but the amount of storage your Lambda has for its quote-unquote local file system is kind of irrelevant in the grand scheme of things. Typically, it's not going to affect your cost. It's really runtime and memory used. So the faster you can run it and the less memory that you can use. So everything that we're going to be talking about today is, I would say, specific for AWS, but it doesn't necessarily need to be. Azure has Azure functions, and there are Rust and Python bindings for Azure functions. Google Cloud Functions or Google Cloud Run both can follow a very similar model. Everything that I'm going to be talking about today and the stuff that is in Delta Lake, the Definitive Guide, centers around AWS Lambda, just because it's kind of the easiest example to explain to most folks. Here's an example Lambda, that I wanted to just point out. In Python, this is literally it. This is a Python file that has a Lambda handler function. I slap that into my zip file, and I go try to run it, and it's going to try to import the Delta Lake file, or Delta Lake module, and then open a configured URL from from S3. In almost every case, though, unfortunately with Python, this is not going to work because you will be missing the Python Delta Lake dependency. And if you've never deployed a Python-based Lambda before, if you need any dependencies that are not already present, it can be kind of a challenge to set up those dependencies. And the Delta Lake library in particular has some specific challenges around packaging that I'll talk about in a little bit. This is the Rust equivalent, largely is doing the same thing. In the case of Rust, I'm certainly biased. I am a Rust fanboy. I helped create the Delta Rust bindings, so Rust is my preferred language. Not the most readable for everybody, but when I see this, I'm like, Rust, this is so wonderful. The nice thing about the Rust Lambda support is you compile a singular binary. Because AWS doesn't come with sort of a native built-in Rust runtime, it says, just give me an ELF-style binary that can run on x86 or ARM, and I'm just gonna run that. So we just have to compile a binary and just give it to AWS and they'll run it. So you can kind of shove whatever you want into that binary. And so this is effectively the equivalent of the previous slide. Some might say Python, it's so beautiful. But it's effectively doing the same thing where we just open up a Delta table and just return some of the metadata about that Delta table in Rust or Python. Relatively straightforward. One of the really useful tools that I think makes Lambda for Delta particularly interesting are S3 event notifications. With S3 event notifications, you can trigger a Lambda to run whenever an object is created, whenever an object is modified, so a new version, whenever an object is deleted, or any other number of events from S3. And if you recall, a Delta table is just Parquet files sitting on S3. This means you can configure your Lambda to be triggered when a new Parquet file lands in that S3 bucket. And this is something that I've used to great effect for very cheap Delta Lake processing. I do want to note this was a limitation that I sort of hit, I would say, halfway through implementing things. You can only have one type of S3 event notification for one type of prefix suffix. So let's say you want to get triggered every time a Parquet file shows up in S3. You can have one Lambda that gets triggered every time a Parquet file shows up in S3, or you can send that event to one SQS. Fortunately, you can also just send that one event to SNS and then use SNS to fan out to different queues to trigger multiple Lambdas. But there is sort of that nuance if you want to build this constellation of really impressive, super cool Lambdas that you kind of have to think about your data flow for these event notifications up front because you can't just configure the bucket to trigger every single one of your Lambdas. In terms of non-S3 event notifications, you can do some interesting things with Delta Lake and non-S3 event notifications. You can pipe Event Bridge into SQS and then go do something interesting. You can receive webhook data directly from the internet and just append that to a Delta table. Kind of any what do they call it? Any input on a Lambda, you can turn into something useful with Delta. But a lot of the examples that I'm going to talk about are using S3 event notifications because generally speaking, I try not to process the data of a Delta table inside of a Lambda because time is money and we want to keep less runtime and less memory. So let me talk about Oxbow. I've included this link. This code is open source. You can go look at it right now. There's lots of Rust there, so be warned if you don't like looking at Rust, but it's beautiful. Oxbow started as something that was going to just process S3 event notifications and append to a Delta table. This is a very common use case that I've seen both at Scribd and a lot of the other companies that I've worked with on the Delta Lake, in the Delta Lake ecosystem. Typically at your bronze layer, you just want to append data. You just have some data coming in from somewhere, you just need to get it to a table, and then we'll do the more complicated merges, joins, and filtering that we need to do. In AWS, there's actually a lot of things that already speak Parquet. If you're not familiar with Kinesis, there's Kinesis Data Firehose, which has an output conversion, and you can tell Kinesis, just put Parquet files in this S3 bucket. Once we have Parquet files in an S3 bucket, we can do something interesting with that. AWS Aurora can export directly to Parquet now, which is interesting, but it can also send snapshots to Parquet. If you use Airbyte's down on the expo floor, you're happy to go, please go talk to them. They've built a really cool product. Or if you use Fivetran or any number of tools that already exist in our data ecosystem, most of them know how to produce Parquet files, and most of them know how to talk to S3. You can build a Delta Lake table on the tail end of almost any single one of those with relatively low effort with AWS Lambda and Python or Rust, or you could just take Oxbow and deploy it. You're more than welcome to. One of the things about Oxbow is as I deployed it and as I started to see how different things started to work in the ecosystem around AWS Lambda and our Delta tables, a number of other Lambdas started to crop up. If you've ever looked at a diagram from AWS, there's always like 9 different Lambdas and queues and arrows and boxes, and they're like, it's just that simple. Oxbow sort of got out of hand in that regard. So there's a couple of other Lambdas there that are worth looking at. Group events just is grouping events based off a key. So if you've got multiple Parquet events coming from an S3 bucket, it'll group them based on the Delta table that they are sequenced in and send that into an SQS FIFO queue. That's useful if you need to avoid lock contention or concurrency challenges with Lambda, which is something I might as well go ahead and mention now. Lambda by default will run up to 1,000 versions of your Lambda at the same time. And so if you imagine an import process dropping a couple thousand Parquet files in S3, your queue is going to fill up with a couple thousand Parquet files immediately, and you might have up to 1,000 different Lambda invocations all running at the same time. And if they're all trying to append to the same Delta table, there will be some problems with that. And so what group events does is it sort of serializes those based off of the table that they are destined to in order to ensure that a file going to one table is processed sequentially as opposed to this like massively parallel Lambda invocation. Glue create and glue sync are relatively straightforward. If you're in AWS, you might be using AWS Glue Data Catalog. Those help synchronize these Delta tables that Oxbow is creating with the AWS Glue catalog. Glue create will just create that entity. Glue sync will update the schema as the schema is changing, because if you've used AWS Glue Data Catalog, you may have experienced the data crawlers, which support Delta Lake. I don't want to throw too much shade at AWS on this, but they don't really support Delta Lake. It's really not a good integration. And if you have a large number of Delta tables, I would recommend finding another way to update your Delta tables in Glue Data Catalog rather than using crawlers. This last one I wanted to call out, this was a recent addition and has become very, very useful, SQS ingest. There are some cases where we actually do want to process data. We don't have something else dropping Parquet files into S3. SQS ingest just listens on an SQS queue, takes whatever messages out, writes the Parquet file, and updates the Delta Lake transaction log. All of this code and more is available to you on GitHub right now. But I'm going to talk a little bit about how this actually is working in production. So real world stuff. So my favorite example of using Delta Lake and AWS Lambda is getting rid of some very heavyweight, expensive, time-consuming ingestion of online transactional data and pulling that into the Delta Lake. So you may have an architecture that looks similar to this. I've seen it at a number of different companies where you've got your online databases, you might have replicas, or you might just read directly from your online databases, and you've got one or more Spark jobs that incorporate a lot of that data, or you've used like Apache Scoop, which is part of the HDFS or Hadoop ecosystem, or use something to slurp all that data in and plonk it into Delta Lake. If you're in AWS, you happen to use AWS Aurora, so there is that system requirement. AWS Aurora is really good for a lot of other things. I strongly encourage you to use it if you're running your own MySQLs or Postgres. But the real big benefit from a data standpoint is that we can export those Parquet files directly. So if you want to have snapshots of your data, your online transactional data in your Delta Lake, or in your data lake, which I think most organizations do, then you've got to get it out somehow, and AWS makes that really easy. So at a very, very high level, and I'm going to walk through each of these in turn, this, I wish I had a laser pointer, but I didn't bring one. Ingestion replicas, or the online database, in order to do ingestion, you need a lot of those. Database servers tend to be big, they tend to be expensive. AWS will gladly charge you thousands of dollars a month to run those things. And so we want to cut those out of the equation and go as simple as possible. And so with Aurora's native export to S3 or snapshot export, we can then start dropping Parquet files into an S3 bucket. The challenge with exporting directly from Aurora is they just dump Parquet files. They don't have any regard for how you believe Parquet files should be laid out on the file system, or what prefix structure your Delta tables need. And so there's another Lambda, and this is also up on GitHub, that just restructures them, just reorients them. A lot of the online transactional data that I need to pull into a data lake has a date stamp component, so that DS, because we're just ingesting once a day, we just need a daily snapshot. And so we just take all those Parquet files and just effectively rename them. It's basically a copy because you can't exactly rename in the right way, but it's basically a copy into the right prefix structure that you would expect to find in a Delta table. If you'll remember from before, DS equals 2024-0401, and then those Parquet files. That restructure Lambda is going to rename those files in S3, which is going to trigger more S3 event notifications. There's S3 event notifications flying all over the place here. Those S3 event notifications end up in SQS, which is where Oxbow can just see those Parquet files and it says, great, there's a new Parquet file. I'm going to implement an add transaction. I actually realized I stepped through this in my haste. I already talked through most of this. I forgot I did a walkthrough, so that's my mistake. So with AWS, the Aurora export, there are these two ways. I haven't seen a cost difference between the two. I think it kind of depends on which direction that you want to go. If you do a direct export, what AWS does is behind the scenes, they spin up a replica for you and do the snapshot export, or do the export of data to Parquet from there. If you do a snapshot export, they spin up a replica from your snapshot, and then they do the export from there. They're more or less about the same cost, and you get the same thing at the end of the day. So depending on which is easier for you, if you already have snapshots, it's pretty simple just to start exporting those to Parquet already. This part, as I mentioned, is just annoying. Any sort of file system layout that Fivetran or Airbyte or whatever is going to output, typically you will need to reorganize that in some way to look like a Delta table, especially if you're using these Hive-style partitions. One of the key things that I should mention in a lot of the architectures that I've deployed this is that S3 bucket is going to be different than the ultimate data lake S3 bucket. One of the useful patterns that I've seen is to have Aurora dump to a bucket that it controls. So your permissions are Aurora can write to S3 for snapshots. That's it. And then you configure S3 bucket replication to where you restructure the files and then replicate those into your data lake bucket so that the replication has writes to your data lake bucket, but the export process does not. I don't have a good reason for that other than I just don't trust kind of anybody. So I want to segment the permissions at every step of the way, especially when there's writes that it might be touching my production data lake. Once that new bucket has those files, it's going to get those S3 events, as I mentioned, and those go into SQS. And then Oxbow can do something really interesting with it. And in every architecture, or every deployment of this that I've seen, I've not seen Lambda cost because Oxbow doesn't touch those data files. So all Oxbow is needing to do is needing to receive the event, which is just deserializing JSON coming into the Lambda, and then it needs to open the Delta table, and there's a rub there, we'll get to it, and then it needs to add a transaction to add to that table. And that typically is very quick. Now, opening the Delta table is where I mentioned checkpoints earlier. You may run into some issues, and you may need to deploy another Lambda or have Oxbow create checkpoints for you. Because if you think about something that's going to be appending, say, tens of times per second or very, very frequently, each time we append, we create a new transaction in the Delta table. And so you go 1, 2, 3, 4. And then when the next Lambda invocation comes, it's got to load the Delta table. So it's got to load the transaction log. It's got to go 0, 1, 2, 3, 4, blah, 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 blah. That can become very time-consuming as time goes on, and that's where checkpoints come in and are very helpful. Those checkpoints allow the Delta log reader to say, oh, I don't need to go back to 0 and replay from the very beginning, I can go to checkpoint10.parquet, and that has my current table state. Or maybe I'm on version 12, then I have to load my checkpoint10.parquet, then version 11 and version 12. But that's where some of the limitations with Lambda and Delta tables really starts to get tricky, is if the size of your Delta table's transaction log starts to exceed the memory or the time constraints that you might have set up for your Lambda. So Oxbow can process terabytes of data, quote unquote, process, but it never sees those terabytes of data. But if the Delta transaction log is 100 gigabytes large, then you might have difficulty loading that in a conventional Lambda. One of the things that I wanted to mention with this, I would say this approach is schema evolution is not quite supported. Oxbow does not read the data files. So if you have differently schema'd Parquet files that are coming through, it's not going to know how to update your tables for that. The other Lambda that I mentioned, SQS ingest, can do schema evolution. In the Delta Lake, Rust, and Python libraries, we can do schema evolution now. And when the schema of the data file changes, assuming that you are loading a data file or loading a data object of some form, it will add new non-null or new nullable columns to the Delta schema as time goes on. But Oxbow, because it's not touching the data files, can't do that. I mentioned there's an opportunity for lock contention when you have like thousands of files happening at once or thousands of files dropping in. With Aurora export, files come in different shapes and sizes. There is no consistency to how those Parquet files are written. And so you may get 1 or 2 very large Parquet files, or you may get a lot of very small Parquet files. And so on the Buoyant data blog, I did talk a little bit about this contention problem, where if you have a lot of events trying to modify a single Delta table at once, it's just unavoidable that you will have contention. Imagine you've got 1,000 Lambdas all running at the same time. One of them has the lock, 999 have to wait. And then number 2 has the lock, and so 998 now have to wait. And that lock wait is just too long for most Lambdas, and they'll time out. The benefit of this architecture, though, is those events coming into SQS, you should be configuring SQS with a dead letter queue. So if something fails to process, you have a dead letter queue, you just go redrive the dead letter queue. You don't lose any data with this approach. The data's already there in S3, it's just a matter of adding those transactions to the Delta log. But when you're running in Lambda, I can't stress this enough, if you're interacting with a Delta table, you may have to change how concurrency of that Lambda is provisioned, or think about how you're going to fan out events that you might be adding to a Delta table. Generally speaking, there's a lot of boxes now, boxes and arrows. This is simpler. There are far fewer things that can go wrong. One of the downsides of replication is at least once a year, replication is broken in a production environment that I'm familiar with. And it's fairly, I would say, fast and simple, especially because the code's already written, right? But if you're wanting to use Lambda to work with Delta tables, I'd recommend you look at the Rust code if you feel like getting involved in the Rust side of things for Oxbow and look at that for inspiration. Or just look at examples that we have for the Delta RS repository on using Python. Effectively with Python, I forgot to move my slides. With Python, the challenges are not in working with Delta tables. There's a lot of really useful examples with pandas, with polars, or just interacting with PyArrow directly that you can just rip straight from Stack Overflow or the Delta documentation and drop into a Lambda function. The challenges with Lambdas typically comes down to packaging with Python. As I mentioned, the AWS SDK for pandas doesn't include the Delta Lake library. And so you might be, you basically have your 3 options: a zip file, which you can shoot a Python zip into a Lambda. It can only be, I think, 5 to 10 megabytes. You can't fit the Delta Lake Python package in there. A layer, all your layers, so you can pull in that AWS SDK for pandas, all of them have to add up to some number less than 250 megabytes. And if you do a pip install of Delta Lake, you will get about 40 megabytes of data, and the AWS SDK for Lambda is about 210, 215. It's dicey. And what I've done in some cases to try to make this work is I've removed debug symbols, I've stripped things out of that package just so I could put my layer with Delta Lake on top of the AWS SDK for pandas. And it's just, I mean, the binaries are just a little too big. So with a Docker image, you can just create a Docker image for your Python Lambda and put that into AWS and it'll run it. I honestly would just recommend that. I forgot, I was just talking. We'll go to that. You lose the ability to edit the file in the web console if you go with the Docker image, but if you've got any number of Python dependencies that you want to incorporate, maybe you've got some esoteric NumPy needs or some other machine learning type Python package that you want to pull in, if you just bite the bullet from the outset and just build a Docker image, then it'll be a lot easier for you to iterate and work with that Python Lambda in Delta Lake. So both pandas and polars are pretty simple to load a Delta table. In this case, this is just loading a Delta table in Python. We have a function called toPandas, which will just spit out a pandas data frame for you. And so on the first line, we're reading the transaction log. So if you run this in your local machine and you're connecting to a Delta table in S3, you will see some time delay because it's actually loading the transaction log, understanding the state before line 2. On line 2, we turn that Delta table into a pandas data frame. And the challenge with pandas is pandas data frames have all of your data in memory. So if you have a 10 gigabyte table, so relatively small, and you do 2 pandas without these filters, forget these filters exist, but if you do 2 pandas, it's going to try to load 10 gigabytes of data into memory on your machine, and on your laptop, that's probably gonna work. In Lambda, it's probably not gonna work. And so we have a couple of optional arguments on toPandas. Polars has a very similar way to work with these things. But we specify filters, in this case, a DS filter. You can also restrict the number of columns that we load into that data frame to reduce the memory footprint of your data frame. And then you can do anything you can do with your pandas data frame. So you can merge, modify, combine them, do whatever you want. And then you can feed that back through. I don't know if I've got the, I didn't put there's a function called write to Delta Lake, or write Delta Lake, excuse me. You can just pass the data frame back into write Delta Lake and update the Delta table from Python. And that's it. Like anything you can do in Python with Delta Lake that's documented today, you can do in Lambda, but you have to be very mindful of your memory. Looking at my time. Okay. There are a number of ways that Lambdas can and will fail. One of the big reasons I strongly encourage you to put SQS or some sort of queuing mechanism in front of your Lambda invocations is because you will run into one of these failures if you're working with a Delta table. Delta tables can run, the transaction log can get bigger as time goes on. So if you imagine that Oxbow case where we're appending, at some point we need to create checkpoints, and that's great. But if you're appending or if you're merging or updating, you're creating redundant transactions as time goes on. And at some point, with good Delta table maintenance, we need to vacuum or optimize those things. And so that you can do in the Lambda. There's some optimization and compaction functions in Python and Rust that you can incorporate. But I wouldn't recommend doing those in Lambda because typically they need to load lots of data into memory. And so a useful pattern that I've seen for that is to have your light, fast merge, updates, appends, et cetera, go through Lambda, and then have a scheduled ECS task or a Databricks job that comes on some period, say at the end of the day, and optimizes that one particular partition. As long as you're optimizing on these discrete partitions, you typically won't have any challenges from a conflicting data standpoint. One of the other things is the runtime by default and the memory by default with Lambda are fairly short. I think it's like 10 seconds of runtime and 128 megabytes of runtime memory. Bump that to 2 gigabytes of memory. The cost is not substantial, like give yourself the headroom. And also putting that that timeout on the function is also very important to align with SQS. So if you're queuing your Lambda from SQS, SQS has a timeout on a particular message that should be aligned with the timeout of the function so that SQS doesn't inadvertently give another function the same data that is already being processed by one of your Lambdas. And I already mentioned the concurrency challenge. And so typically using Lambda, especially with Python, crazy easy once you've already got the Docker thing set up. It really comes down to how fast can your operation run and how much memory does it need. I tried to blitz through as much as I can because there's lots of code available for this, and using Lambda with Python in particular is very simple. Every example that uses Delta Lake plus Python that exists on the internet today, you can take and just drop it straight into Lambda. There's nothing special needed. With Rust, there is a little bit more nuance needed just because of the packaging that needs to happen. All right, thank you very much, everybody.